Hey, all right. So now that we've seen how to do a double integral over a rectangle, we're going to see how to set it up over more general regions. And what we need is what's called an elementary region. And so I'll informally describe this as just being two flat parallel sides which are joined by graphs of functions. So this is best probably illustrated by a couple of examples. So here's the kind of thing that I mean. Suppose we have a plane region that looks something like this. Okay, so I've got these flat parallel sides. So this is here's from like A to B. And then I've got these graphs of functions. So this is like maybe some function d of x, and maybe this is some function down here that we call c of x. And then I can think of this region as being a whole bunch of slices going in this direction parallel to the y-axis. Yeah? And so then the idea is that I would set this up as an integral where first, to figure out the length of those green slices, I'm going to integrate my function, whatever my integrand is, let's just call it f out of complete lack of imagination. And so first I want to make these green slices. The green slices go in the dy direction. So I'm going to be doing this as an integral first with respect to dy. And each one of these slices is going to start on the bottom and go up until we get to the top, like that. So it's going from the c of x curve to the d of x curve. So I put c of x as the lower bound and d of x as the upper bound. All right. And so then that gives me, so at this point right here, this is the height of the green slice at x. So x is this coordinate down here on the bottom axis. And so then I'm going to take that and integrate it from left to right, sideways, to pick up the whole thing. So let's just say, first off, if I look at this height of the green slice at x, I could call that f of x, capital F. And so now I'm going to integrate that from endpoint to endpoint. And then that's going to give me the entire integral that I'm interested in. Okay, so that's one type of elementary region. So that's an example. Then I could also have something like, let's see. This. Okay, so now I've got this flat line parallel to an axis down here at C, and this flat parallel line up here at y equals d. Yeah, so this is y equals c, y equals d. And then I've also got these graphs of functions going between them. So let's call this one here. Now, this is the graph of a function of y, right? So it's varying as we move it in the y direction. So I'm going to call it a of y. And this one over here also varies as y changes. So I'm going to call it b of y. And so then if I were setting up the integral here, now I'm looking at decomposing this region into a bunch of slices that are going between the green curves parallel to the blue, like this. And so let's see, so I would take my integrand and I would integrate it, and we're going from the lower green bounding edge to the upper green bounding edge in that direction. So I'd be going from a of y to b of y. Those are the ends of my bounds. And we're integrating right now in the direction parallel to dx, the x-axis. So this is dx first. And that gives me the, let's call it g of y. So this much right here, this is going to be the width of the green slice at y, where y is this height right here. Okay, so now that I've got that width, the size of that slice, I integrate the length of those slices from bottom to top. So I'm going to integrate from c at the bottom to d at the top, and we're picking these up in a direction parallel to dy. So we integrate from c to dy, and that would be our total integral. So these are both good regions, or what we call elementary regions. If you have something that does not come like one of these, then you have to cut it up and partition the domain so that it does look like it. So for instance, suppose we had something that looked like this. Okay, so here I've got my flat parallel sides, but I cannot think of this as a bunch of slices because this is not a function of x down here on the bottom. It breaks the vertical line test, right? So if I were going to integrate a function over this region, I would have to partition it. Like maybe I could split it right here, and then I have a bunch of pieces. So now I've got an elementary region here that's orange, and I've got an elementary region here that's blue, and I've got an elementary region here that's red. So I would have to cut it up. So similarly, if I had something that looked like this weird fish, then now it's perfectly fine that on the left side here, I have this, my flat parallel side is a point. That's okay. That's not a problem. But what's a problem is this situation over here. I would have to cut this into at least 3 pieces so that I could have my blue elementary region down here and my green elementary region up here, and then my purple one over here. So let me just emphasize again, this part is not a problem. That happens all the time. All right, so a little bit more formally now, the definition of what I mean by an elementary region is some domain in the plane that looks like xy pairs, such that it can be written where x is between 2 constant values and y is between 2 functions of x, or the other way around, where we have x is between 2 functions of y and y is between 2 constant values. So what we saw previously with the example of a double integral over a rectangle, this is just a case of one that's an elementary region either way, because what we're doing is we've got everything between these flat parallel sides from A to B, and then between this function of x, which is actually just a constant function, so c of x is just c, this is constant, and d of x is just d, this constant right here. So let's see. And of course we could set it up the other way around as well.